Today we'll explore what a salt bridge is, why it's needed in galvanic cells, and how it works. First, let's understand what a salt bridge is. A salt bridge is a U-shaped tube or porous membrane filled with an inert electrolyte solution like potassium chloride or potassium nitrate. Its main purpose is to connect the two half cells of an electrochemical cell while maintaining electrical neutrality. Let's visualize a typical galvanic cell, also known as a voltaic cell. Here we have two half cells, a zinc half cell on the left, which will be our anode, and a copper half cell on the right, which will be our cathode. Between them is our salt bridge, a U-shaped tube containing a solution of potassium chloride. The salt bridge allows ions to move between half cells without direct mixing of the solutions. Now, why is a salt bridge necessary? Let's see what would happen without one. At the anode, zinc metal undergoes oxidation, losing electrons and forming zinc ions. This reaction is zinc solid goes to zinc 2 ++ 2 electrons. As this happens, positive zinc ions accumulate in the left half cell. Meanwhile, at the cathode, copper ions undergo reduction, gaining electrons to form copper metal. This reaction is copper 2 ++ 2 electrons goes to copper solid. As copper ions are consumed, there's a buildup of negative charge in the right half cell. Without a salt bridge, these charge imbalances would quickly halt the reaction. Too many positive ions in the anode compartment and too many negative ions in the cathode compartment would create opposing electric fields that prevent further electron flow. This is where the salt bridge comes in to save the day. The salt bridge contains an inert electrolyte like potassium chloride, whose ions don't react with the half-cell solutions. As the cell operates, ions flow through the salt bridge to maintain charge balance. Chloride anions from the salt bridge move toward the anode compartment to balance the positive zinc ions. Potassium cations from the salt bridge move toward the cathode compartment to balance the negative sulfate ions. This ion migration keeps each half cell electrically neutral, allowing the redox reactions to continue and electrons to keep flowing through the external circuit. Let's summarize the key functions of a salt bridge. First, it completes the internal circuit by allowing ion flow between half cells without allowing the half cell solutions to mix directly. Second, it maintains electrical neutrality in both half cells by providing ions that can move to balance charge. And third, it allows continuous electron flow through the external circuit by preventing charge buildup that would stop the reaction. Remember, without a salt bridge, your galvanic cell won't work for long. The salt bridge is essential for maintaining the continuous flow of current in electrochemical cells.